Swayam Prabha. Digital India. Educated India.
Welcome back. In lecture 29, we will, now that we have learned about the basics about machine learning and the different typologies and all, now we go back into EDA, and what we are doing over here is we are continuing the lectures which we have started earlier, and this is part 3 of data analysis and visualization. But these lectures are more towards model building, because now that we are moving into machine learning, we have to build models and all. But before we start building models, some basic checks has to be done. So these are some of the concepts that we will cover. Stats model, functions and objects, we will learn about that first, and then we will move into back into data analysis and visualization. And within that we will cover multivariate correlation analysis, variance inflation factor, and of course we will try to also visualize this multivariate correlations and all, or how these are related through pair plots. So these are the different functions and objects for the stats model library, and now we are introducing libraries one by one in the different lectures as per the requirement or as per our use. So over here you can see that this particular library is focusing on the different models that we built. These are the all machine learning. Some of these models are also machine learning models as well. So that means like linear regression, time series analysis, you will find both in sklearn or in this the stats model in both these libraries. And the first model is the first categories of functions is model results and summaries, such as fit statistics. Once we fit a model or a regression line, that standard output that comes out, that is the different measures of how good the accuracy or fit of is, that should be given. And it also gives the summary statistics using the summary function. Then we have ordinary least square, weighted least square, and then generalized least square regression that could be done using this sort of calling these functions. Then there is GLM models, Gaussian, and then there are different regression for non-normal outcomes via distribution families and link functions. So that means what we do is we can also look into non-normal functions and we can feed them to the data as well. Then there is the discrete choice and limited dependent variable models such as logit, probit, MN logit, Poisson, and so on. And logit probit models, these are also very important for classification tasks. Then there are time series models, ARIMA, SARIMAX, WARE, AutoReg, exponential smoothing. These are all related with doing time series predictions. Then there are certain functions for get, forecast, predict. That means once the model is built, we will apply that model to do the prediction. So this is where these functions comes in. And then we do different sort of tests for each of this model, like t-test, f-test, vault statistics and all. And so those functions could be also called. Then continuing, we can check heteroscedasticity, normality. We can do ANOVA for linear models, and then we can do again different kinds of covariance test. Then we can have custom like very GMM, other kinds of more custom models. Then there is this KD density estimation and kernel regression, those kind of models. Then there is MANOVA that we can test. We will also learn MANOVA in this lecture itself. And then there are some data preparation utilities such as add constant, like for when you are developing a model, you can add a constant, and dematrices and so on. Now, to continue with EDA, we will use the same data set we were using earlier. So this is the urban air quality extended.csv file, where we had PM 2.5 and in certain other gases such as NO2, SO2, O3, which are being, the data for that is recorded at each air quality recording stations. And this varies as per the different areas, that is what sort of land use is there, residential, commercial, industrial. And also we have taken some other predictor variables such as population density, traffic volume, industrial activity, which is an index, of course, if from 1 to 5 or 1 to here we can see 1 to 5, but it could 1 to 6 value. So so this could be the different categories of industrial activity, and based on all this we can predict what would be the emissions that will happen. So moving into from earlier we did univariate relationship, then we also did covariates and between two variables, and then bivariates, and then between two variables, and then we are now moving into multivariate correlation analysis. So basically what we do is whenever we are trying to work with many variables together, trying to build a model, right? So we are trying to predict something based on a few other variables. We should make sure that we should look into the relationship between the variables that we are trying to use to build the model. So it is a so multivariate analysis, correlation analysis. It looks into the relationship among multiple variables, particularly 3 or more, simultaneously to find complex patterns. And what we need to do is we do this so that we understand which are the predictors which are more strongly predicting the target variable. So we can identify those first, and then we will check for multicollinearity, that is if the predictors are also strongly related with each other, that is one change of one will influence another one, right? And then if relationships are linear or monotonic, that is the relationship linear, increasing constantly, or it's a flat rate, or it's a gradually increasing value like monotonic but in the same direction. So there are two measures that we actually use to measure this. One is Pearson correlation and the other is Spearman rank correlation. Pearson correlation is used when we are going for checking this relationship among the linearly related variable, right? So that is when relationships are linear and the variable is continuous and there is no extreme outliers, we go for Pearson correlation. And Spearman rank correlation, usually when relationships are non-linear but monotonic and then outliers could exist, then we will go for Spearman rank correlation. So obviously this is rank and this is actual value, right? So here we actually try to determine the ranks and see how those ranks are correlated. So multicollinearity occurs when two or more independent variables are strongly correlated with each other. Now there is no problem with this, but both these variables cannot be inside a model. Why? Because then it becomes difficult to isolate the individual effect of each of this model, each of this feature. So that means there are two features which are very correlated. Now which is affecting what is very difficult to say if both of them are there in the model. So so what happens is when there is multicollinearity, for example, say between traffic and industrial activity, because both of them influence the amount of emission, so we can say both of these are also correlated. So what happens is during analysis of the coefficients may become unstable. That means in one run you get a set of coefficients, in another run it may be different. Then there are standard errors will increase, the prediction errors will increase, and the signs can even flip. That means we know that particular variable is to be either positively or negatively related with the predictor variable, but we see the sign is coming as negative or opposite to what it is supposed to, or counterintuitive. So that means if both of them are there, because the effect one has taken more, is putting a larger effect, the other one is becoming negative, even though both are positive, right? So a variable can have low pairwise correlation yet still be highly collinear when combined with others. So what happens is, after we do this correlation analysis with the data, we are more or less able to discard the ones which are related with each other and so on. But sometimes what happens, even though there is low pairwise correlation and not apparent from the statistics, that is the basic statistics like Pearson and so on. So in that case, what we have to do is, when combined with many things, it becomes collinear, right? So because of some overlapping effects or causality and so on, right? So in that case, this is not adequate to just limit ourselves to. That means beyond pure cell correlation, we have to further look into ways to understand this. So this is where VIF also comes in. So VIF analysis is done to just to check if there is within the variables, within the predictor variables, is there a lot of relationship or not. So coming to an example, Python example, of course, this is the Python program where we are doing a correlation analysis. The data set used is the same one that we have been using, the PM 2.5 prediction, that data set. So we import pandas, import matplotlib, import cborn as SNS, and then we load the data set into the data frame. So this part is pretty standard. Then what we are doing is we are creating this numeric variables from this particular file, that is PM 2.5, NO2, SO2, everything which is numeric. We are now storing them inside this vars. So and all categorical variables are not included, such as area and all those things. Now, once we have stored that in this vars, what we do is we so first from vars we are storing it in a numeric matrix first. Why? Because the subsequent method we utilize will require it in that form. And then what we are doing it, we are calling the function x.core, because x we are already giving here. So x.core, and based on the syntax we have to do this particular step. And then when we are calling x.core and method equal to Pearson, definitely it is going to store the correlation coefficients in core underscore p. Similarly, I can call x.core method Spearman, and we can store it in corr underscore s. Now I am printing the values, that is Pearson with PM 2.5/n, which is the next line. That you can find Pearson with P.2.5. Then we are going to the next line. We are printing the values like core. This first what we are doing is we are this core p PM 2.5. We are we are correlating with, and we are also going to that means what we are all the variables that we have taken over here. So what we are doing over here is in core p PM 2.5 sort values ascending equal to false/n. What we are doing is we are taking the results or the coefficients that is being generated over here core underscore p, and we are just printing them one after another, and we are sorting them as per ascending equal to false. So that means it is in descending order. And then we are also printing spear, and that is happening over here. So you can say that when we have taken this particular this thing, so PM 2.5, then SO2, NO2, all this is correlated with PM 2.5, and we are seeing that all of them, these are the values which are coming from those. And it's here it's very, very correlated, all these values. And then there is also industrial activity index, which is also very highly correlated. Traffic volume vehicle per day, it is moderately correlated. And then population density per square kilometer, it is negatively correlated. And not only that, the value is very small. Now we can do Spearman in the exact same way. The code is more or less same. Now core.s is x.core into method is already we have given Spearman. And then what we are doing is we are also plotting this particular values. That means once we have printed the Spearman this ranking, over here you can get the values PM 2.5, this 1, 1, 1, these are equally important, and then this COMG, this carbon monoxide is coming, then industrial activity is 0.94, which is almost same as this one, and traffic volume is particular, this which is a little bit improvement. So I think it's better to go for Spearman in this particular case, and population density also remains more or less same. So once we have done that, then we create the plots where we can do a heat map. As you can see over here, sns.heatmap. Now what it does is it actually takes chord underscore p, that list of list of coefficients, and then it shows it in a heat map, because everything is related with everything. So over here, what we have done is, while the coefficient list contains every correlation coefficient between each pair, we are printing in the first step only the PM 2.5, how it is only this part, that is how PM 2.5 is related with all the other variables, right? So the others are not printed like this. It is given in this particular plot. So we are generating the heat map, and then plot title we are giving plot.show, plot.figure, what should be the size of that plot, and then what should be shown in the plot.heatmap, core underscore s, annotation true, FMT equal to 0.2f. All this, based on this 2f is basically the rounding up of the coefficient values to the second decimal point. So we will see the effect of that. See here, nothing is rounded off. The entire value is given. And then at the plot title, and we can give the command for plot show. So this is how it shows. Now see, all the variables are only till 2 decimal points, right? Earlier it was multiple points. So over here you can see the heat map where each the cell shows correlation between the two variables, of course, and the larger magnitude usually is a stronger association. I will not say darker, because that is not how you perceive darker, that is again another thing. But what we can say is, if all the coefficient values are given in within 2 decimal points, and we can just see and take a look and see what is related with what. For example, population density per square kilometer and industrial activity index. You see, this is minus 0.43. Now minus is basically negative. That means when one increases, the other decreases, and vice versa. And minus 43 is moderate level of risk of collinearity, right? So if it is between 4 to 0.7. So because it is borderline, I can keep it in the model, but if I feel it is not suitable, I can even remove it, right? Now same goes for correlation analysis and Spearman analysis, right? Now population density and industrial, what we find from this after interpreting this particular model is population density and industrial activity have moderate collinearity risk, and other than that, all gaseous pollutants are very strongly related to each other, and there is a risk of multicollinearity if you are taking all of this together to do some sort of prediction. And also these are strongly related with industrial activity, which can be used to predict one of these particular gaseous emissions. Then we come to variance inflation factors. As we discussed earlier, sometimes what happens, even though individual collinearity is fine, we cannot see multicollinearity, but maybe the result is not that good, or there may be some other indications as well. And then what we do is we go for the variance inflation factor. Now VIF measures how much the variance of a coefficient is inflated, because the predictor can be explained by other predictors. That means the idea is to measure, that means how that particular coefficient is being represented in a particular model. Is it overinflated or not? And is it, if I take only those variables which are taken as the predictors and I do a correlation, I can find out, or a regression model, then we can, based on I can find out which ones are more related and so on. So VIF measures how much the variance of a coefficient is inflated, because the predictor can be explained by other predictors. Relationship among predictors do not on the dependent variable. So we are in VIF we are trying to look into the relationship between the predictors, not the decision variable is not important. And when it is high, when the VIF value is high, that basically means that we cannot separate individual effects of predictors in regression, even if the overall model is a good fit. That means we cannot trust the model. That means the model shows everything is fine, it's a nice regression line, maybe R-square values also are proper, but if you go in to check the VIF and all this thing, you will see that the model collapses more or less, because individual effects varies, and That means this high VIF value actually it separates this individual effects of predictors to see that okay, which one is having a more better role or which is a better fit of the model. So the VIF value range starts from 1 to 10, as you can see. 1 is no multicollinearity, 1 to 5 is moderate, usually acceptable. Greater than 5 is high multicollinearity, and greater than 10 is, of course, a serious problem. That means we should never go beyond 10. But others we can still take a call. Now, how it is measured? It is measured, it's not that difficult. VIF j is equal to 1 by 1 minus r squared j, and r squared j is how well variable j is explained by all other predictors in that overall equation, right? So let us take an example. We have PM 2.5. Let us assume that x1 and x2 are the two variables, and x3 are the three variables which are predicting it. So beta 0, beta 1, beta 2, beta 3 has to be determined, and E is the epsilon is the error term over here. Now x1 is traffic volume, x2 is industrial activity, and x3 is population density, right? Now what we do is we will take the three predictors together: traffic volume, industrial activity, and population density. And then what we do is we actually do predictions like this. X1, we take one of them. Suppose we are doing VIF for traffic volume. In that case, we take x1 is equal to, this is another equation we are forming. And then once we have done that, we can determine the r square value amongst them, all these parameters. And once we get the r square values or the coefficient of determination values, which is a measure of how well the regression model explains the variability of the dependent variable. And so what we can do is, r square is basically, it measures the proportion of variance that is being explained by a particular model. So that actually is a indicator of how strong the model is in the first place. So once we have the r square, once we do the analysis like this for every predictor variable, how it is related with the others, we will be able to get a r square value, and that we have recorded. When we do with traffic as the decision variable or the target variable, then the r square value is 0.65. If it is industry, it is 0.9. If it is density, it is 0.2. So these are the different values that has come, and as I told you, that is when the value is more than 10, then we will, after of course we compute this particular statistic. If the value is more than 10, we can actually remove this from our or this particular combination of features and all is not going to work, or rather that these are very collinear and so on, that we can explain. So again, coming back to the Python program for this, import panda as PD from stats model dot stats outlier influence import variance inflation factor. So this is the most important line in the model. That means you should know from stats model I can get this particular function. And df equal to pd dot read underscore csv is basically loading the file into the df data frame. And finally, again from df data frame, we are loading it into a variable x, and we are taking all the variables except 2.5. So PM 2.5. Now why? Because PM 2.5 is the one which is not being challenged here. We are looking only into the predictor variables, not the target variables. And then then we create a data frame to create the data values. There's VIF underscore df equal to pd dot data frame, and then VIF underscore df within that a variable equal to x dot columns. That means whatever variables you want, we can do that. For each of these variables which would get printed, of course, we are storing the value of x dot columns. X is basically this one, x, and these are the columns of that. And when VIF df is equal to variance inflation factor x values I, for I is range x dot shape for 1, then we are going to finally print VIF df. Now what is happening over here is values are converted, values converts the predictor data frame x into a numpy array. So this values function does that, and then what it does is the ith location, when it is running in a loop, of course, for I in range x dot shape, that is for every position it will pick up that value and then it would store there. Then then it will find the variance inflation factor of that particular value, right? And this happens for all the values over there. Now coming to output, we can see that we have the variables that has got printed first: NO2, SO2, CO, O3, population density, traffic volume, industrial activity, and then the values of VIF is also given over here. So VIF is obtained by for each variable by regressing it against all the other predictors, as we have discussed in the previous slide over here. Now, both correlation and VIF are statistical numerical diagnostics, but if I want to visualize something, that is how things are related with each other and all, we can go for a pair plot over here. And as you can see in this image, we can see this pair plot where at the x-axis wise you will get all the distribution of each of this particular you will see that how each one is related with its own self, but at everywhere else you can see, like for example, industrial activity index and then PM 2.5, what is the trend of the data, right? Are these two data sets for different land uses? We don't know. And similarly for population density and PM 2.5, you can see in some cases when population density is increasing, maybe these are the three land use type, that means we are also getting higher values of PM 2.5. But in some cases it is not. So there is also a challenge in this regard. So pair plot help us to visually determine linear versus nonlinear clusters, outliers, and heterogeneity for each of the land use types. And you can see in this program, import Seaborn as SNS, import matplotlib.pyplot as plot. We are loading the data in the data frame DF, and then we are storing the variables same as earlier. Then we are just calling the SNS pair plot, where we are giving it different parameters, such as what kind DF vars is the ones which is going inside over here. DF vars, this is from where it is coming, so all the column list is going inside, and then we are using this as KDE to do the analysis over here, and then it is ready to plot the data. So once that is done, then plots.surface, this is for printing, and then plot.show function is called, and this is what you get. So these are some of the references that we have used. To conclude, exploratory data analysis through multivariate correlation, VIF diagnostics, visualization, and other tests provides statistical insights and rigor necessary for reliable regression and machine learning model development. Thank you.